lecture 5. And I want to give one more example of, this kind of perturbative test. But this time I want to give an example in flat space, okay? Because I think this is instructive, in fact, covering the same kind of physics that we had earlier. But if some of you got confused by, unitaries and projectors and the vacuum and so on, we'll use slightly different language to elucidate the same physics, so it might be helpful. Yeah, the ground state is always entangled. So the question is does this fact the Hilbert space is not factorized mean the ground state is always entangled? No. The ground state is always entangled even in an ordinary quantum field theory, right? So sometimes people say, very formal people say, well, the Hilbert space is not factorized in a quantum field theory. But that's kind of not a very physically deep statement. Because, entanglement is different from lack of factorization. What we are saying here, what we were saying last time, was, we had some observables here, and those same observables could be detected by something here. This is not entanglement. We are really saying it's the same observable. So if you make a measurement here, it collapses the wave function for this guy as well. Okay? So we are really saying the observables here are the same as the observables here. It's a much deeper problem with lack of factorization. It's not to do with some UV issue of, the fact that there's a lot of entanglement in the ground state. So please differentiate between the issue of entanglement and what's happening here. Entanglement is something, if you have two qubits, they might be entangled, and that's fine. But here we are saying something else. We are saying we don't have independent qubits here and here. It's not that they entangle, they are the same. There's some degrees of freedom here that are actually the same as the degrees of freedom here. So it's not a question of entanglement. I mean, entanglement is one part of it, but it's not in the end, the result is much stronger than just entanglement. Okay. But by the way, sorry, can I ask also, Jesse, when you're running the poll, what was the result of this poll this time? It was that now 25% said it's advanced and 75% said it's correct, but nobody said it's easy. I see. Okay, fine. So that's fine. Okay, so let me give you one more example of these perturbative tests that we discussed, but this time in flat space. Okay, so it's the same. We're going to play the same kind of game. Okay, so imagine the following setup. I'm now doing the same thing in flat space. Yeah. And let 0 be the Minkowski vacuum. Okay. And let me excite it with a state which looks like e to the I lambda integral f of r. Okay. And I'll work in these retarded Bondi coordinates using this retarded time. You shouldn't get confused. It's just more convenient instead of using t to use this coordinate u. We have r and we have omega. Omega is the direction on the S2. Okay. Okay. So when I do the smearing, I sit at u equal to 0. And I act with some unitary operator. So I have a single scalar field, a massless scalar field, which is coupled to gravity. And I act on the vacuum with this operator. Okay, this is a unitary operator. And this f of r has some support in 0 to r0. Yeah. Okay. So where does this unitary operator act? You would have thought that it acts here, right? Because it acts near, u equal to 0 for some finite value of r. If you think of what it's doing, it's kind of acting on some light cone here. Okay, so it's acting, looks like it's acting in the middle of space. Now you could ask, well, let's trace it. It's a massless field, so signals propagate at the speed of light. So you could have thought it'll create a state of this kind. Okay? Now the question I want to ask is, let's say we had some observers who were living here, and they were making measurements in this red region. Could these observers detect what, this function f of r was? Okay, is it possible for them to determine what f of r is? Of course, in a local quantum field theory, they can't do that. It's impossible for them to detect what f of r is. But the game we were playing told us that, in principle, these observers can detect f of r. And this is a similar example to the one we had in ADS, except I'm going to now tell you how these observers can do it in a slightly different way. by just using a 2-point correlation function rather than talking about, unitaries and projectors of the vacuum. Okay. So what these observers need to do is, I'm going to imagine that, they can, measure this unitary and they can act with it for different values of lambda. Okay. So that's one additional thing we are giving ourselves, because we just want to understand, how this could be possible in principle. Okay. So we are simplifying things a little bit. So we are allowing these observers to work perturbatively in lambda. Okay. So what the observers need to measure is the following correlation function. H this correlation function, let me just capture this, notice, is something that these people are in principle allowed to observe, right? Why? Because notice that H is an observable here in the red region, right? This is H. And then I'm making a measurement of phi, but this time I've taken R prime off to infinity. Okay? I'm also going to take U prime to be very large and negative. Okay? So I'm going to take U prime to be in this red region. Okay? So this is a correlate. They're just measuring a 2-point function of some observables in this red region. Okay, the state is F, it's generated by something here, and these guys are measuring some correlator in this red region. Okay? If this was a local quantum field theory, then this correlator would be completely unaffected because this unitary is acting at some space-like separated region to what this is. Okay. However, here we can easily do the calculation and we can see what will happen. You see, if you were to do the calculation, you would find, and this is just limit as R prime tends to infinity, okay, R prime, and the d by d lambda is just picking up the first order term in lambda. So let's just write that, right? It's 1 minus integral f phi, okay, h phi u prime r prime omega prime into 1 plus I lambda f phi, okay, times 0. Okay. Now this is a simple calculation to do because you have to pick up the first order term in lambda. You have some lambda, you have a lambda here and a lambda here. And so, you can easily do this calculation. And all you have to do is just commute the h through this. And once it comes here, it will give you 0. So I'll just tell you what the result is without doing any algebra. I'll just tell you what the answer is. The answer turns out to be that this answer just turns out to be, it's a simple 2-point function calculation. Okay, it's something that you can do. It just turns out to be this. Okay. The reason the answer didn't depend on this omega prime was because for simplicity, I'd taken my state to be spherically symmetric. I'd taken f to depend only on r. Of course, you can make it, angular dependent, but it doesn't give you any particular insight for what we have here. Okay. Notice the interesting thing that's happened. This 2-point function, even though we are measuring it here, is affected by the unitary that acts here. Okay. This is a property that's unique to gravity. Why is it affected by this unitary? Because the Hamiltonian doesn't commute with this and, Hamiltonian fails to commute with this phi. And that's why this 2-point function is affected by this unitary here. Okay. Now, this answer, in fact, you can check if you know this answer in this red region. So U prime here is just something in the red region. You can completely determine what f of r is. And how do you determine it? Well, you know this answer for very large U prime, right? Because U prime here is very large. You just expand this out and you will find that this just looks like, 2 to the n by 2 pi times U prime to the n plus 2 sum over n, okay, integral r to the n f of r. Okay. So if I measure this for different values of U prime, I can pull out the different coefficients of the different inverse powers of U prime. Each such coefficient gives me a moment of f. Once I know all the moments of f, I can get f as accurately as I want. Okay, if I want f more accurately, I have to measure higher and higher inverse powers. But as you can see, you can reconstruct f to arbitrary accuracy via this process. Okay. This is another example of the same physics we were discussing. If you have observers who are space-like separated to some unitary excitation in a theory of gravity and only in a theory of gravity, these observers can actually make some measurements which involve correlators of the Hamiltonian and other observables. And using this, they can reconstruct completely what the state in the middle was. Here, the state in the middle was completely characterized by a single function f. It was a very simple state. We're just doing this to give an example. And I'm showing you how, by measuring this 2-point function, you can completely characterize the state f. Yeah. Is this clear, what I said right now? You can go and do this calculation at home. It's a simple calculation to do, right? Just take f to be the state. And you have to work perturbatively in lambda. And, we're working, and just take f to be the state and just compute this 2-point function. Okay? And realize that h is the Hamiltonian. It's observable here. Okay? And if you do this, you will find this answer. We're taking the limit r prime goes to infinity. That's what is telling us these observers are here. And you will find the answer. It's easy to see the answer completely determines what this function f is. Yeah. Okay, good. So now, once again, in this case, you could have asked, how did information jump? Did it go from here to here? Did it go from here? How did it jump? And of course, the answer is it didn't jump superluminally. The answer is that in gravity, the excitation had to have originated on Scri minus, right? Okay. And because it had to have originated here, and therefore, right, it leaves behind traces at infinity that can be picked up later. Okay, this is exactly what happens also with the Gauss law. How does information about the total energy get picked up? Well, because when the matter falls in, it modifies the metric at infinity, right? And therefore, you can determine the energy. Now, what I'm telling you is in the quantum theory, you can determine not just the energy, but all observables. Okay? You can determine all aspects of the state. And that's what we're seeing here. Yeah. So this is not, you should never think that the information is jumping from here to here. There's no jumping of any information happening. It's just the fact that, the constraints force all information to continue to live here. It came in from here, so it had some effect at r goes to infinity. And the information, doesn't fall in. There's always some observable at infinity that you can determine, that you can measure, that will determine what the state is completely. Are there any questions about this? Okay. If not, then I'm going to ask, let me go to a slightly different topic, right? Before I go to the information paradox, I want to explain something slightly different. Okay? So I've been explaining to you how gravity localizes information unusually. Okay? In fact, are we right separately expansion of Q prime? Sorry, can you explain what that question means? Are we right separately expansion of U prime? So Gokula Krishna has a question, which is, are we writing separately expansion of U prime? Can you please explain what that means? I didn't understand what that question means. Jesse, maybe you need to unmute him.
So can you hear me?
Yeah. Go on. Yeah.
I didn't get how you're like getting the using moments that FR, because already we don't know FR, right? So what do you mean by like writing as a summation in moments? Is it like
No.
expansion?
I'm measuring this correlator. This is what I'm measuring. Then this
Okay.
correlator, the answer for this correlator became this. Now, if I measured at different values of U prime, I can determine the different moments. I can determine the powers. I can expand this answer, right? I know it for U prime very large, like near minus infinity. So I can determine what the different powers of U prime to the n plus 2 are, right?
Okay.
Using that now, I'm an experimentalist. I measure this and I do an expansion of this in u prime to the n plus 2, right? And
Oh, okay.
coefficients are the moments.
Oh, got it, sir.
Okay. I mean, I'm not an experimentalist, as you can see. I can hardly get my computer to work, but in my dreams, yeah. Go on. Ansh has a question. Yeah.
Yeah, so I wanted to ask, like, is this similar to the yesterday's calculation where they switched on a similar source at their end and then continued on?
Yeah, it's similar, except I'm using slightly different language because I got the feeling that maybe people are getting confused by sources and so on. So this is a correlation function. It's a kind of calculation you do in quantum field theory. It's a 2-point correlator. It's very similar. It's in flat space as opposed to being in ADS, but very similar.
Oh.
Okay, are there any other questions? Okay, I want to say one more thing before I go on, which is actually an important thing to say, right? The unusual localization of information in gravity that we have been discussing for now 2 lectures is not always important. Okay. So I want to tell you now that there are some cases where this is not important. Okay. So for instance, one place you can read about this is in this paper. Yeah. And I want to tell you, an example where this unusual localization of information is not important. Okay. Okay, let me give you one, before I go to this paper, let me give you just another example of where this unusual localization of information does not even apply, where the effects we've been speaking of don't even apply. Okay? I've been telling you that, the Hilbert space doesn't factorize and so on. But remember, everything I've been saying works in the case where we have a region R and the observers are in some R bar that surrounds R. Of course, there's another situation you could consider. For instance, the situation that you could consider, so I'm giving you some examples where this is not important. A system you could consider, which is the kind of system we consider in the Ryu-Takenagi formula, where R is like this and R bar is like this. Okay? Here, the Hilbert space does factorize. You see, in this case, it is not true that information in R can be determined by information in R bar. That's not true, right? Because remember, everything we were doing had to do with the Gauss law and measuring the energy of R and correlating quantum fluctuations in the energy with other observables. But here, the observer in R bar does not surround R. So they cannot measure the energy in R. Okay? If you would like to think in terms of gauge invariant observables, you can take an observable and you can draw a Wilson line that dresses it to this side. Okay? You can take an observable, draw a Wilson line that dresses it to this side. Okay. So in this kind of configuration, the Hilbert space does factorize. And that's why when we speak of the Ryu-Takenagi formula, it makes perfect sense to speak of the entanglement entropy of one part of space with the other part of space. Because the configuration there is not this kind. It's never this kind where, except in one case, I'll mention about islands a little later, where the region R bar surrounds R. Okay. So this unusual localization of information, you should know when it's important. It's important in situations like this, not in a situation like this. Okay, let me give you another example. Sometimes, even in a situation of this kind, this localization of information can become unusual localization of information, can be hidden quite well. Okay. What is that case? Well, let's say we have a heavy classical. So now let's go back and talk about this case. But say we have a heavy classical background here. With e to the s states. Okay. Then it can indeed be very hard for an observer outside to determine, what the state of R is. Why can it be very hard? Well, you just go back to the kind of protocol that we were constructing for the observer outside to determine what the state in R was. And you will easily see, and this is something that I discussed at the end of the last lecture, that it will become, if you have a heavy classical background with e to the s states, then it becomes exponentially hard. The observer outside needs an accuracy for the e to the minus s to distinguish what is happening in the interior, okay, to distinguish states in R. I hope this point is clear. You see, what we were doing was we were making different measurements, right, of different correlation functions, and we were measuring correlators, and then we were saying, well, I measure these correlators outside, and then I use those correlators outside to reconstruct what's happening in R. However, you could say, what if there are lots of possible states inside R? There are e to the s possible states inside R. Then, clearly the observer outside needs an accuracy of order e to the minus s to distinguish these possible different states in R. Okay? There is no getting around that fact. It will be clear, if you were to take the protocol that we had and just ask what happens, if you ramp up the energy so that you have more possible microstates, and you will see that, you will need to have this accuracy in order to be able to reconstruct what's happening inside. Is this intuitively clear? I'm happy to explain this a little bit more, but I hope this is intuitively clear. If you have e to the s states, I ask you which one of the states it is, then, exactly. In the words of the previous lecture, would we be dealing with exponentially more xi? Exactly, right? You would need all these you would need an exponentially large number of xi's, because how did the protocol go, right? It said, let me find the overlap of G with one basis, then a G with second basis element, G with third basis element. Well, all these different microstates, they just, they all have similar overlaps. They just have overlaps that differ by some exponentially small amounts. So clearly, if I play that game, it will become exponentially hard for me to determine what's happening in R. Okay. Okay. However, there's one important point. Okay. Sometimes, and I'll say it intuitively, sometimes two states might be easy to distinguish for a local observer in R, for an observer in R. But still exponentially hard for an observer in RBAR. Okay. Why is this the case? You see, the observer in R has some preferred basis, right? Maybe they have some local observable or some local source. So let's say you have a heavy classical background, and on top of that, I add a little bit more energy. I do something. I add a small dot on that. Now, if you have an observer in R, this observer can go and probe that region and can ask, is there some local excitation there or not? However, for the observer in R bar, what the observer in R bar is doing is not directly probing these observables. What the observer in R bar is doing is trying to reconstruct the overlap of the state G with all these different basis vectors that they have constructed. And, these two states, this state, if you have the presence of this or the absence of this, might be pretty similar in terms of those basis vectors. And the reason is that the observer in R bar is not using a basis that is necessarily natural for R. What the observer in R bar was doing, if you just go back and look at the protocol we had, they were just constructing some basis of states that they had, and then, they could calculate the overlap of G with that basis. But, physically, the observer in R might have some basis where they might say, this corresponds to an excitation of a photon, and there are other possible changes of the microstate that don't correspond to anything. Right? When we say there's a meaningful excitation, what we're saying is not that we acted with, some random operator, but that we acted with a specific operator that created some specific combination of phases or, excited some particular degrees of freedom. Now, the observer in RBAR has no way of knowing that, that there's some natural basis in which you change the microstate from this one to this one. So there might be some states which are easy to distinguish for an observer in R, but still exponentially hard for an observer in RBAR. So the general estimate is that if you are in a region RBAR and there are e to the s states inside some region, for the observer outside, it's just always exponentially hard to determine which of the states they're in. In the example that we did last time, S was basically 0 because the number of states that we were looking at was low energy states. And so we were not looking at a background which had a large entropy. Okay. So these are 2 points which I want to emphasize. I can explain this in a little more detail, although if you like, you should go and look up the paper. But maybe given the time, I'll go on and go back to the question of black holes. But I wanted to mention this issue that the unusual localization of information in gravity is a very important physical phenomena. I think it's one of the most important things we learn by thinking of the black hole information paradox. But it's not always important. And 2 cases where it's not always important are first this, which is a case where you study the Ryu-Takenagi formula. And second, the case where you have a heavy classical background with e to the s states. And then it's possible to define some approximately local operators by dressing basically to this background that commute to very good accuracy with operators in RBAR. Okay? These operators are sometimes called state-dressed operators. There's also this discussion of algebras in gravity and how you get a type 2 algebra. And a lot of that really is physically doing this, introducing some heavy observer. That heavy observer can then define some local operators around that observer. Okay, good. So now, are there any questions about this? I can explain this with some more equations, but I wanted to go back to discuss black holes. But if there are more questions, I'm happy to explain this here. What is the name of the formula? What formula are we referring to here?
Just on the bottom, the sphere, or where you have the R. Yeah, you said the name of the formula. How do you write the name?
I said the Ryu-Takenagi formula.
Oh.
This is this is called an entanglement wedge. And the RT formula, the Ryu-Takenagi formula, computes the entanglement of one side with the other. But to compute entanglement, you have to have factorization in the first case. Yeah.
Thank you.
Okay. Okay, you're welcome. Are there any other questions? Okay, good. So let's now go back and discuss the question of black holes. Yeah. So you see, the answer that we now want to give, just going back to the question of black holes, remember, let me remind you, what was the discussion that we had about black holes, right? The first discussion we had, this was, now a couple of lectures ago, so I'm going to go back to the discussion, was that, you have a black hole. And, it's formed from some collapse. And the first discussion was that, Hawking computed that if you look at some modes here, which are A omega, Hawking computed that A omega dagger was 1 by 1 minus e to the minus beta omega. Okay. And, this itself might suggest that the state in the future or state outside was a mixed state. Okay. But then we said at the beginning that, this can't quite be right, because if I add order e to the minus s by 2 corrections, then I could make these correlators perfectly consistent with correlators in a pure state. So just computing these correlators by brute force, you'd have to work very hard before you would be able to prove there's a paradox, and certainly Hawking didn't even take into account 1 over s corrections. Forget about order e to the minus s by 2 corrections. Right? Okay. However, Hawking had a slightly more sophisticated argument. The more sophisticated argument went as follows. Right? It was what he called the principle of ignorance. And he said, look, here's a region R and here's a region R bar. Right? Now he said the principle of ignorance was the statement the observer in R bar is ignorant of the state in R except for the mass charge and angular momentum. Now, if you look at this configuration, you see that the state in R will never come into causal contact with R bar, right? Because the black hole will evaporate away. Therefore, the observer in R bar should trace over possibilities in R. Which means you get a mixed state for R bar. Okay. So this argument is not relying on a brute force calculation of correlation functions. Rather, it's relying on the no-hair theorem, and it's relying on the causal structure of the space-time and saying, well, clearly the observer in R bar should trace over possibilities in R because of the causal structure. And in fact, Hawking said this is the basic principle of quantum mechanics is that, the observer in R bar is ignorant of the state in R. Okay? However, now we've been building up to this for some time. It's clear that this is not correct, right? So sometimes people say, where is the error in Hawking's argument? Well, this is the error in Hawking's argument. And really, if you go open Hawking's paper, you will find, this principle of ignorance being very important, and this is exactly what is being said. But you see, this is incorrect because this is assuming that gravity localizes information the same way as ordinary quantum field theories. And we've spent now a lot of time trying to explain why that is not the case, right? So in fact, we should replace the principle of ignorance with the principle of information, right? So let's shrink this. What we have is that observables in R bar completely fix the state of R. So if the Hawking radiation is formed in R bar, knows about R, knows about the state of the infalling matter, right? This is the result that we spend some time establishing. Now you might say, well, but to leading order, the Hawking radiation doesn't. Indeed, it doesn't, right? Because to leading order, all that the metric knows about, if you just look at 1-point functions of the metric, then 1-point functions of the metric, so this is the correct statement, right? Let me put this here. If you look at 1-point functions of the metric, they know only about the expectation of the Hamiltonian. But what is the parameter that controls corrections? Corrections are controlled by you see, we have Newton's constant, and what's the energy parameter? Quanta. One quanta. And this is 1 over s. So if you look at 1 over S suppressed corrections, let me now go to the next page. So leading 1 over S corrections already carry more information this is kind of obvious, in fact, if you think about it. We think of black holes as being statistical objects, but what are the leading 1 over S corrections? For instance, you could ask, what is this? Of course, to leading order, this term is 0 if I divide it by expectation of h squared. But, if you start looking at this term to subleading order in S, then you see this tells you about the fluctuations in the energy of the black hole. By now, we are used to thinking of black holes as statistical objects. This kind of correlator is different for a microcanonical black hole, for a black hole which is prepared with microcanonical spread, and for a black hole which is prepared with canonical spread. And this information is available in the geometry at order 1 over S. In fact, why is this available? Because remember, we said in the quantum theory, this is not the same as h squared. An observer outside, you don't have to go inside, an observer outside can determine this just by looking at the metric and looking at quantum fluctuations of the metric. So you see the no-hair theorem automatically fails when you include quantum effects. Okay? We don't need to do anything fancy to make the no-hair theorem fail. The no-hair theorem automatically fails even at leading order in 1 by S. We see that you get more information than just the total expectation value of the energy. Okay. Higher 1 by S corrections contain more details of the infalling matter. And the discussion that we just had, well, how high do you need to go in 1 over S to verify the purity of the state? Well, you need to keep track of e to the minus S terms. Keep track of purity. Okay. And this is not surprising because to verify the purity of the state, you do need to go to order e to the minus S, and only then can you verify the purity of the state. Right? So you see, there's a clear error in Hawking's argument. One doesn't need to invoke any exotic mechanisms, like invoke any exotic physics to do this. We just have to correctly impose the constraints of gravity. And when we correctly impose the constraints of gravity and quantum mechanics, we find the no-hair theorem fails. The geometry outside, observables outside have more information at leading order 1 by S, higher in, and if you go to higher and higher orders, and finally, if you go to order e to the minus S, these observables have all information about the interior. Right? Now, let me just say that if you remember, a couple of lectures ago, I proved this in terms of a formal result. So this is not some hand-waving estimate we are making based on the games that we were playing in the last lecture, but we formally proved that all observables at infinity have information about what's happening in the interior. And in fact, I now want to prove a simple formal result explaining that an observer at infinity can always verify purity of the state, which I'm now about to prove. Okay. There's a question about we had a second case when the unusual localization doesn't apply. No, remember in the case of here, what was important was that it was not that the unusual localization didn't apply. It was more that the observer outside needed an accuracy e to the minus S to determine different states. So if you decide that the observer outside is not allowed that accuracy, let's say you force the observer outside to coarse grain their measurements. You say, sorry, boss, your experimental apparatus is not that powerful. You're not going to be allowed to measure e to the minus S. Then, of course, they will not be able to detect what's happening in R. But if we restrict the scope of the observer outside the black hole in this way, then there is no point in speaking of the information paradox. You see, if we are going to say we will not allow the outside observer to make measurements to e to the minus S, then information is lost, right? That's obvious. That's like saying, if you burn a piece of paper and you don't keep track of fine-grained details, information is lost, right? There's nothing surprising in that. The point is, if you do keep track of fine-grained details, then is information lost, right? So it's very important that the second case that we're talking about doesn't apply to the information paradox, because if we try to apply this case where we say we'll coarse grain things for the observer outside, then there's no point in speaking of the information paradox. There's no information paradox at all because you coarse grain, so you lost information, right? So there's nothing surprising. So you have to allow the observer outside exponential accuracy. And indeed, our estimate is precisely, if you allow them exponential accuracy, they will be able to determine the purity of the state. Yeah. But does that answer the question? If there's more questions on this, I'm happy to answer this. Okay, I want to prove a slightly more formal result. This is going to go back to the result about operator algebras. I wanted to prove. The statement I'm making that the observer outside can always verify the purity, you can in fact frame this in terms of entanglement entropy on Scri plus. And then I want to spend some time speaking about other perspectives on this. Okay. So let's say we look at, this is Scri plus. Okay. And we look at a region which is minus infinity to some u naught, right? Now, how do we define an entanglement entropy? Well, we can define entanglement entropy as follows. Let's look for some rho u naught, okay, which belongs to the algebra of operators up to u naught, such that for all a belonging to this algebra of operators up to u naught, these are the kinds of algebras I defined 2 lectures earlier, okay. We have the property that trace of rho u naught a is equal to the expectation value of a in a state. So we are in some state. Corresponding to that state, we can define a density matrix which has this property. And then we can define S of u naught is equal to minus trace of rho u naught log of rho u naught. Okay, that's how we would define the entanglement entropy. If you're very formal, then let me point out that maybe it's you might want to look at the relative entropy rather than the entanglement entropy, because then there are no UV divergences to worry about. Okay. So study relative entropy if you want to be mathematically precise. For mathematically minded. Okay, but I'm going to be somewhat simple-minded and I'll work with the von Neumann entropy because these issues of, the UV issues are kind of irrelevant to what we're talking about. But as I said, you can frame the whole discussion in terms of relative entropy. There's no problem. Okay, now remember, what did we say? I proved a result which said any element of a u naught can be approximated arbitrarily well by an element of a epsilon. What was a epsilon? A epsilon, this was the algebra of operators from u equal to minus infinity to minus 1 over epsilon. This was this algebra of operators, right? So even as we are on null infinity, and we try and consider larger and larger intervals, we can just pick the density matrix once and for all. We can always we don't have to pick a density matrix differently for different values of u0. We just pick the density matrix once and for all from this a epsilon. What does this mean? We can just pick independent of u0. What does this mean? This tells you that S U0, remember this is the formula for S of U0, is independent of U0, and therefore d by du0 of U0 is equal to 0. Okay. Well, what does that say? That says that if you compute the entanglement entropy on Scri plus, if you started with the pure state, you stay with the pure state. If you started with the mixed state, you stay with the mixed state. It just stays like this. It just stays constant. Okay. So if you started with the pure state and the entanglement entropy of 0, the observer outside can always verify the purity of the state. What was Hawking saying? Well, Hawking was saying the entropy will go up like this. Okay. This is the curve we get by correctly implementing the constraints of quantum gravity. Okay. Okay, this is a formal result, a formal version of what I said earlier, which is, look, we've been talking of the unusual localization of information. An observer outside who has access to all these observables can determine at all times that the state inside is pure. And, the Hawking's argument relies on a principle of ignorance, on the no-hair theorem. That's false in a theory of quantum gravity. We gave many examples of how it is that information that looks like it's inside a region can be accessed from outside the region. This is not in violation with causality. You should not think that the information is jumping from inside to outside. Rather, as the infalling matter falls in, it modifies the metric and other observables outside. And the constraints of quantum gravity always force that information to remain outside in sufficiently precise observables. How precise? Well, the precision has to be e to the minus s. But if you do keep track of observables that are that precise, you will always be able to determine that the state is pure. Okay. Okay, so are there any questions at this point? I now want to go on and talk a little bit about the page curve in the last part of this discussion. But first, this was one of the main physical points I wanted to make. So if there are questions, I'm happy to take them here. Okay, if there are no questions, then I worry I lost people. Either it's completely clear to everyone, which is possible, but I'm suspecting these ideas are new for at least some of you. So if there are no questions, then maybe this is lost. Even if it's a question that you think is a dumb question, I would encourage you to ask it. I'm sure many others have the same question. Yeah, go on, Kiran. Go on, Kiran. Do you have?
Yeah, okay, thank you.
Yeah.
So, how does this work with these models like in hidden preschool, where you insert some message inside the diary and then it comes like you have some message in diary and it comes out like that?
Yeah. Clearly, this Hayden Presskill model and so on is all assuming that information is still localized in the usual way. So I'm going to say a little bit more about the page curve and in what setup you can make these things precise. However, I think this is frankly speaking, I think the running theme through the literature is to just assume that if you throw something inside the black hole, it's lost to you. Well, of course, if you throw something inside the black hole, it's harder to read than it is that it was earlier. But in the Hayden Presskill scenario, what you do is you throw something inside and then you wait for information to come out, and then you keep track of exponentially small corrections, and you start asking, when does information about this diary come out? So, you throw it in at different points in the black hole's life cycle, and then you ask, when does information come out? In those questions, you do keep track of e to the minus s corrections. But if you do that, then if you are going to keep track of e to the minus s corrections, then you should be very careful about notions like, I threw the diary in and it went in. So I think there's conflation in many parts of the literature, which is that there's a mundane notion we have, right? Which is if you don't keep track of e to the minus s corrections, in most things in everyday life, we don't, right? So if you throw information inside the black hole, it's lost. It's lost. Why? Because it's now exponentially hard to get it. But if you do keep track of e to the s corrections, which you do want to keep track of in the Hayden-Preskill protocol, otherwise you can never read the diary because the diary comes back completely scrambled, right? So if you are going to keep track of that, then you should be very careful of notions like throw in. Then, you know, even after you throw in the diary, you can always read the diary if you keep track of those information. So, I think that's a good example of a situation where, you know, we are not being careful of the unusual localization of information in gravity. I'm going to give some other examples now.
Yeah, okay, thank you. So the diary is also like not local. It's also not localized. I mean, like,
yeah, I mean, not, you see, well, you have to be careful of what accuracy you're working in. If you say you're working with accuracy which is order 1, right, which is what we usually do, we don't keep track of exponentially small corrections in the atmosphere around us, then the diary is gone, it's localized inside the black hole. But if you are going to work at that level of accuracy, you'll never get the diary back. You know, the diary will, it's not the diary will bounce, the information will bounce back or anything like that. The diary will go into the black hole, it'll get completely scrambled in the Hawking radiation, and you will never be able to read it again. Okay? Or you could say, well, I want to be able to read the diary again, so I am going to keep track of corrections of size e to the minus s. If you do that, then the picture that you have of space-time is very different. Then you start seeing the fact that the space-time is holographic. So then if you, even as you throw the diary in, you don't lose information. You know, you always have track of that information for someone who's sitting outside. So, you know, this radial direction, which is where you're throwing things in and kind of trying to make things harder for yourself, is something that emerges when you coarse grain. If you don't coarse grain, you keep track of fine grain information, then, you know, you don't have this extra direction. Then the information is always localized at infinity. Right? So you can't throw stuff in. And indeed, you can always read what's happening in the diary. Okay? So it's subtle because it's something that we are not usually used to thinking of, because we usually, you know, see there's an extra direction. But in the end, you should remember gravity is holographic. And therefore, information about the diary is always available outside. It doesn't go in and get lost and then come back again.
okay, thank you.
Yeah, S being constant for all U0 is the statement that unitary evolution is safe. That's right. So if S was 0 in the beginning, it would be 0 later. That's right. That's right. You neither lose nor gain information as you go along, a square plus. I'm just responding to another question in the chat. Okay. If there are no other questions, then I want to spend the last part discussing something slightly different. Is there a question, Juan? Yeah, go on.
Yeah, but pure state has 0 entropy.
Yes. So pure state, if it has 0 entropy, then it will stay 0 entropy. All we proved was that ds by du0 was 0. So if it was 0, it would stay 0. If it was not 0, it would not be 0. You know, we just proved that ds by du0 was 0, which is the statement of unitarity, really. Unitarity doesn't tell you started with a pure state. Maybe you started with a mixed state. If you started with a mixed state, you would stay with a mixed state.
Right. And why PU is in the previous slide is independent U0? I didn't get
it's
it.
Because look how we defined U0. We defined it by saying, look for a density matrix, so that which depends on U0, which has this property. Right? And then you compute S of U0. This rho U0, in a usual quantum field theory, you would pick rho of U0 from this algebra A of U0. It would be different for different U0s because you get more and more elements in the algebra. So you can pick different rho U0s. Remember the result we proved earlier, which is any element of A of U0 for any U0 can be approximated arbitrarily well by an element of A epsilon. Remember that?
Yeah.
So I can always pick the density matrix once and for all from A epsilon. I don't have to pick it differently for different U0s because all these U0s, in fact, they all belong to this algebra. I can always approximate them arbitrarily well by an element of the algebra here. Right? So the fact that I am allowed more observables, which would have been useful in quantum field theory, is not useful in gravity because all observables at a later time can be approximated by observables at this time here. So I can just pick rho once and for all independently of U0. That tells you that d by d is U0 of S of U0 is 0.
All right. Okay. Thank you.
You know, if this is sounding strange to you, by the way, let me give you another example. You're familiar with this. some of you, I'm sure, have studied ADS-CFT, right? Let's compute the entropy of the boundary theory. Here we compute it as a function of time. Let's compute ST. Well, what is d by dt of ST? Well, it's 0. Because the boundary theory, if it was mixed, it was mixed. If it was pure, it was pure. It doesn't change with time. Okay. The boundary theory always has all information at all times. This is the analogous statement for flat space. Yeah. That, if you, in the boundary theory, as you change things, it's not, let's say I allow you observables from a big band. It doesn't matter because all the observables are already available at this slice. So if I allow you observables from here to here, it doesn't give you any more information. Whatever information you had in a time slice, you have. So it's not like measuring more time on the boundary tells you that the state is any more pure. Even measuring a small amount, 1 instant of time on the boundary is enough to tell you the state is pure. And measuring bigger and bigger sandwiches of the boundary is not helpful in telling you the state is pure or not. This is the analogous statement for flat space.
Thank you.
Excellent. So now I want to change gears and I want to discuss a little bit the page curve, which is also something that you've heard of. So of course, famously, the Hawking curve is prediction information is lost, but there's also the so-called page curve. What did Page say? Page argued information would first be lost and then come back. And then recover. This is related to these, these Hayden-Preskill arguments are, in the end, a refinement of this page argument. Page argument is the most basic argument of this kind that you can make. The way these arguments go, I don't have time, unfortunately, to go through them in detail, is, but it's very closely related to the kind of integrals that we did in the first, in the first or second lecture, where remember, I tried to tell you how close are pure states to mixed states. And I introduced this Haar random, this Haar measure on the set of states. And I tried to average things. That's the kind of argument that goes into deriving the page curve. What does the page curve say? Well, the page curve, the basic argument, the mathematical argument in the page curve is the following, right? Take a system and divide it into 2 parts, right? One which has n parts and the other which has m parts, okay? Then, and the total number of degrees of freedom are nm, okay? Then you could ask, while keeping this constant, let's keep this, while keeping n constant, if you vary m, how does the entanglement entropy of this subsystem, of the left subsystem, vary? Okay. So I'm plotting SL as a function of n. Okay. I'm going to take n to be small 1 to m, to capital N, and I'm going to keep this product fixed. Okay, so as I increase n, I have to decrease m at the same time. This is the basic mathematical result that's done. You take a system, you factorize it into 2 parts, and you ask how does the entanglement entropy of one system, with the other system behave if you factorize it. Well, you see, at the beginning, there are almost no degrees of freedom in n. Therefore, you find that the entropy here is 0. It keeps rising, okay, till you're at roughly, maybe I should plot a function of log n here, okay, till, you're at n is equal to square root n. At that point, what happens is that it's in fact the entropy of m that starts becoming important. Once n has become very large, once it's become almost here, then, if the whole system is pure, then actually it's the entropy of this that starts dominating. So what happens there is that the curve starts decreasing. Okay? So by the time you reach the largest possible value of n, which is when n is equal to m, the entropy has gone back to 0. This is the page curve. The page argument is, of course, correct. Is there a question? Juan, you have a question now, or you already asked the question? I'm assuming you already asked it. You have a question now? Yeah, go on. Yeah.
No, it's previous question.
Okay, fine. Thank you. Yeah. So you see, the page argument is completely correct. If you take a non-gravitational system, you factorize it. It's a Haar random averaging argument. It's completely, there's nothing wrong with it. What is wrong is to apply it to a black hole and assume that the black hole is behaving this way. So the way Page applied the argument to the black hole was, he said, you have a subsystem, the black hole is one subsystem, the radiation is the other subsystem, and this is what is happening, that the black hole is becoming, smaller, and the radiation is becoming larger. So initially you start off with, the radiation being very small and the black hole being large. Then you move this side, and at the end you start off with the radiation being very large and the black hole being small. That was the basis for Page to get this curve. Okay? But notice this is assuming once more that there's a factorization of the Hilbert space into something outside, something inside, and that you have a wall that's moving. And that is not correct for a black hole. Okay? So the Page argument, if you apply it to understand, how does information emerge from a black hole, also relies on the same issue of assuming that information is localized like ordinary quantum field theories in a theory of gravity. Okay. So also relies on factorization. Okay, this is the original Page argument. Now, I'm sure many of you are familiar with the fact that there has been a lot of work recently on deriving the Page curve for black holes. So you might say, well, what is that? Right? Is that wrong? And of course, the answer is it's not wrong. And I now want to explain what are the calculations that are done to define the Page curve for black holes. Okay. In its original form, the Page argument clearly doesn't apply because, it assumes once again that the Hilbert space factorizes into something inside and something outside. Okay. So is this point about the Page argument in its original form correct? I now want to explain what is done when people do calculations of the Page curve, in which there's been a lot of work in the recent literature. Are there any questions about this original Page argument? Okay. So now I want to explain what is done when people derive the Page curve. Okay. The way people derive the Page curve is the following. Okay. Usually these computations are done in ADS. Okay, so take an ADS black hole. Yeah, it's like going from pure state in N to pure state in M. No, actually the entropy of N is 0 in the beginning, not because it's pure, but because it's empty. Okay. And the entropy of N is 0 in the end because it's pure. So on one side it's empty, on the other side it's pure. Okay. For M it's the opposite. M is empty on one side and pure on the other side. Yeah. Okay. So let's look at how these Page curve computations are done. The way they are done is as follows. Take a black hole in ADS, okay, and this is the boundary of ADS. Now the boundary of ADS, we think of as, when we think of ADS CFT, we think there's some non-gravitational field theory which lives on the boundary of ADS. Okay. Now we couple this theory to a bath. So the physical picture we have is that even though you had the infinity of ADS, you kind of extended it, and now you added on a bath here. Okay. So this is a bath, and this is a non-gravitational bath. Okay. In this bath, so here we have gravity. In the bath, we do not have gravity. Okay. Now we make a division in the bath here. Okay. This is some imaginary interface. Okay. Now we ask, what is the entanglement entropy of one side with the other side? Okay. So now we ask, what is let's call this region R and let's call this region R bar. Well, notice this question is a purely non-gravitational question. The fact that there was gravity in ADS is actually completely unimportant because, ADS-CFT tells you can replace the gravitational degrees of freedom with some degrees of freedom on the boundary. So in fact, this whole system you can think of as a system of a CFT, which has one boundary here, which was originally the boundary of ADS. This kind of system is called a BCFT. Okay, it's a CFT with a boundary. So this is just an ordinary non-gravitational system. In this ordinary non-gravitational system, we now ask, what is the entropy of R with R bar? Well, okay, so, so we divide the path into two parts. Yeah, go on, Juan. There's a question. Yeah.
Interior, it's also boundary, right?
I beg your pardon?
The interior, it's also boundary.
The interior of the black hole?
I mean, there's two circles.
Oh, there's no boundary. Oh, sorry. This is infinity. This is not a boundary. Sorry. The outside, there's no boundary. The outside extends out to infinity. The boundary is just inside. Okay, so it's like taking a CFT on a plane and cutting out a disk in the middle. Yeah.
Okay. Mm-hmm.
Entropy of one part. This, of course, obeys a page curve. Why does it obey a page curve? Because, this entropy obeys a page curve because this is just an ordinary non-gravitational system. The fact that this eventually came from a black hole or something is not important. This is just an ordinary non-gravitational system. Now, what is nice about these calculations, I think these calculations are nice, is that we can compute the entropy of the bath using the gravitational dual. Okay. I wanted to explain in these lectures a little bit how this calculation is done, but unfortunately, I'm not going to have time to do it. But there are many lectures online that you'll find that will explain how this is done. Okay, this is done basically by generalizing this Ryuta-Kiyanagi formula that I just mentioned some time back, and you can use that. And there's a geometric computation that lets you compute the entropy of the bath using the gravitational dual. However, so the calculations are nice, and they're correct. And there's no objection I think anyone has to the technical aspects of the calculation. However, what one is computing is not the entropy of Hawking radiation. We are computing the entropy of one part of the bath. Now, the words that are given are, well, we call this part the Hawking radiation. Why? Because, it looks like you had this non-gravitational theory. It corresponded to some black hole. So it looks like the radiation went here. However, the critical difference is that now the radiation has been completely captured in a region where gravity has been switched off. So it's not surprising that now you're getting a page curve because all this unusual localization of entropy and so on, of information and so on was all made sense when you were in a gravitational region. Here, this bath is non-gravitational. Okay? So it's not the way Hawking radiation would or should behave in our world where we don't switch off gravity. But if you were to do this kind of setup where somehow, you find a way to switch off gravity, or, these are mathematically well-defined things, then, you would indeed find this. So there's a mathematically well-defined computation, but it's really the entropy of one part of the bath with the other part of the bath. So the way I like to think of these calculations is they're like ADS-CMT calculations, okay? Calculations. Which is we ask a question of interest in a non-gravitational theory, and we answer it using gravity. Okay, but this is a question of interpretation. Okay, I mean, I don't, everything I said, I think right now is not controversial. But people will say that, well, this is actually a good model of how Hawking radiation should behave. I think that, this is not a good model of how Hawking radiation should behave in our world, because our world is gravitational. But those are questions of whether these are good models or not good models. But it is the case that these computations are really computing some entropy of a non-gravitational bath, and they're using gravity to compute it. And the computations are correct, but whether we want to use the word entropy of Hawking radiation or not is not a question to which there's a scientific answer. And there are various discussions in the literature about this. Okay. You have a question? Yeah, go on.
CMT, what is the meaning?
I beg your pardon?
CMT.
I was meaning ADS condensed matter correlators. CMT means condensed matter theory. Sorry, if this is a reference to something that you're not familiar with, forget about it. There's a part of the literature that has tried to ask, we do, you can ask, maybe you look at some interesting condensed matter system, and then you try and ask, can you find a gravitational dual to it? And then you try and answer a question in the condensed matter system using the gravity dual. So gravity gives you a technique of answering questions which are of interest in the non-gravitational theory. And that's kind of what is happening here. We are answering questions which are of interest in the non-gravitational theory using gravity. But the question that's answered in these page curve computations is not directly of relevance for Hawking radiation, I think, because it's answered by adding on this non-gravitational bath. Yeah. In what sense is the page time relevant to the process of black hole evaporation in our universe? I would say that the page time is not very relevant for the process of black hole evaporation in our universe. Of course, there is a time, there is a physical question of when the black hole completely evaporates, which is maybe twice the page time. But the page time itself, it is to me not clear that the page time itself in our universe, which is gravitational, is very relevant for answering the question of when information comes out. I would say in our universe, either you keep track of e to the s corrections or you don't. E to the minus s corrections or you don't. If you keep track of e to the minus s corrections, you will be able to verify purity at all times. If you do not, then you will, not be able to verify purity even after the page time. So it is not clear to me that in our universe, where gravity is dynamical everywhere, you don't have a non-gravitational bath, that the page time is directly relevant. Yeah. Okay. This is a matter of some discussion, I should say, just to be clear. There's some discussion you can find in this. In fact, there's some non-technical discussion that we did with Jeff Pennington just a few weeks back on this. You're welcome to go look at it, and you'll find various discussion in the literature as well. So the discussion is not really on the technical aspects. Everyone is clear that these are the technical things that are happening. There's a non-gravitational bath in these calculations. We do the calculations. The question is, are these models good or accurate for our world or not? And that is a matter of some debate. But what is being done in the models, I think, is not a matter of debate. So we can ask whether physically it would be the case, for an observer, what are the natural observables? Is it somehow the case that the natural observables see a page curve, or do they see all information at all times? And that's something, we can discuss. And as I said, if you'd like to see a discussion with the other point of view, there's a discussion we recently had with Jeff Pennington. It's on a podcast hosted by Vasudev Shyam. If you search for it in YouTube, you'll find it just a couple of weeks ago. Yeah. Okay, let me say a few more things, okay? The first question you could ask is, sorry, is there a question? Yeah, Gokula Krishna, yeah.
Yes, sir. Does it mean, since you're saying once we keep track of e power minus s corrections, we can get a pure set? Does it mean that we have solved a paradox kind of?
I think so. I think we would say this original version of the paradox you have solved. Now, there are other refinements of the paradox, which unfortunately I will not have time to get into. But this basic version of the Hawking paradox, I think we now agree that we have understood how to fix this basic version of the Hawking paradox. Yeah. I don't think there's much discussion.
So what the page curve concept actually, why we are then introducing it?
Well, so the page curve was historically considered to be the correct answer, right? So there's also some history about, first of all, how did this discussion go historically? It's worth appreciating some of the history of the subject. When Hawking came along and said, well, black hole evaporation is not unitary, that was not a very popular perspective for a long time, because people felt, well, quantum mechanics should work, it should make sense, and there's some error in the calculation, and that error in the calculation will somehow fix it. Now, what was not realized, of course, at that time was this unusual localization of information in gravity or anything else. But then Page came along and said, well, if you were to implement quantum mechanics correctly, this Page's computation is maybe 20 years after Hawking, then, you would find the Page curve, right? And then certainly, many influential people in the field said, if you go look at lectures in the black hole information paradox from the 90s, they said, well, when would you say the paradox is solved? When you have found the Page curve of Hawking radiation. So you should somehow find a way to correct Hawking radiation so that you find the Page curve, okay? Now, I would say now that we understand the unusual localization of information in gravity, the Page curve is not the right target to shoot for. Okay? That being said, you can change the question so that the Page curve remains the right answer. And what is done in these computations of the bath is this. You take a gravitational theory, you couple it to a bath. So this is gravity, you couple it to a bath. And then you ask for a Page curve across some interface in the bath. So the system does have gravity. It has a black hole. It also has a Page curve. Okay. But I think we've changed the question a little bit because we wanted to get the Page curve as an answer. So my feeling is that some of the interest comes from this history that we thought that the Page curve should be the right answer. And so we've changed the question to get that answer. And I think that the physics we are really learning from the information paradox is that information is localized unusually, and therefore both Hawking's argument and Page's argument suffer from the same error. Okay, just to emphasize, Page's argument is completely correct for a non-gravitational theory, but the application of it to black holes, I think, suffers from the same error as Hawking's argument does. Okay. But it was interesting, and in these setups you can compute a Page curve using gravity. This is my understanding of how things go, but as I said, I should be completely clear that this is not universally shared, what I just said, and I welcome you to go and look at the literature, and you should make up your own mind on this. Yeah, Kiran has a question.
Yeah. So even in this case of island, let's say if I start with the mixed state, how does the Page curve will look like? Like if the black hole is
well,
mixed.
it depends on how mixed the state was. It's a question of how mixed the state was initially. I'm not sure what quite you're referring to. How does the entanglement get transferred and so on.
And like if I start with the maximally mixed state, I mean.
Well, what was maximally mixed?
The original black hole that collapsed into the black hole.
Sorry, and then what would you be asking?
Yeah, like the final entropy should still, like final state should still be maximally mixed, right? I mean,
correct, because if it was entangled with something else, it will remain entangled with something else. Correct.
Yeah, but in the Page curve, like in this island formula, it seems to be always dropping down. Like
no, that's not true. If you apply the Page curve correctly to the case where the initial system was mixed, it won't drop down. Of course, it will saturate at some point. No, it's not like the island formula will give you the wrong answer. If you ask the right question, the question if you frame it in a non-gravitational bath, then it'll always work.
Yeah. Okay.
I want to explain two things now. Okay, the first thing is, in these Page curve computations, I want to first ask, how does information even enter the bath? Okay, that's a question you can ask. So just to say, by the way, there's no contradiction between anything I've said and the Page curve computations. There's no contradiction in anything I've said. It depends on which question you want to ask. Do you want to ask the question of, what happens here? What happens in the gravitational region, or do you want to ask the question of what happens in the non-gravitational region? Depending on what question you ask, you'll get different answers. Either the information is available at all times, or it emerges after the Page time. Okay. So first I want to ask this question, right? How does information about the black hole enter the bath? So this is, a question sometimes people worry in this island computations, how does information about the black hole enter the bath? Because it looks like we have an ADS black hole, and this is the bath. Someone could say, the black hole was here in the middle of ADS. And how did the information jump here? If you read, there's criticism of some of these page curve computations. I want to explain, in fact, how the physics that we have just discussed recently helps you understand how the information enters the bath. Right? So the answer is the following. Imagine a two-step process. In step one, we just have an ADS black hole, okay? No bath. Well, then we studied, this is, as we know, and as we've been discussing for some time, all information is at the boundary. It might be available in some very scrambled form, but it's always there at the boundary. Okay. Step two, add the bath. So now we have ADS black hole. Now we added a bath around it, right? So this is my non-gravitational bath. Well, now it's clear how the information entered the bath. It was already in the boundary, right? So it just flows locally. The information just flows locally from the boundary into the bath. So the information doesn't jump from the middle of ADS or from the island into the bath. The information is already at the boundary of ADS in the first step, and it flows into the bath. So what this is telling you is that the physics that we have discussed about the unusual localization of information and gravity is also secretly important in these page curve computations. Now you can further ask, how does information flow from one part of the bath to the other part? And that's, of course, completely local, and it follows the page curve. Okay? But you see, the fact that information was available at the boundary of ADS is important even in these page curve computations, because if it had not been available at the boundary of ADS in the first place, it would not have been able to enter the bath. Okay? If it was stuck somewhere in the middle, it would indeed not have been able to enter the bath. Okay? So, if you read, for instance, there's this criticism, there's a nice paper by Emil Martinek called Trouble with Paradox, which raises this criticism. And indeed, if it had been the case that the information was sitting in the middle of ADS, then there would be a problem. But once you appreciate the unusual localization of information and gravity, you see it's natural that the information enters the bath. Okay. Okay, is it clear what I just said? Okay, let me now make one last point, and then I will stop. Okay. I'm going to ask a question which maybe some of you thought of or didn't think of in the same setup. Okay, this is my ADS black hole, and this is my bath. Now I said, well, the information enters the bath, right? So in fact, it flows across the interface here. This is my interface. I can compute a page curve, right? And I said the information goes from here and then it flows out. However, what does the island formula tell you? The island formula tells you, in the end, there's some island that sits in the middle. But maybe some of you are not familiar with the island formula, but I'm just going to tell you what the result is, and I'll ask you a question later. It turns out the answer is, you look at this radiation region, and there's an island, and information about the island is available in the radiation region. In particular, information about this island is not available in this region. Okay, it's not available at the boundary of ADS. Now you could say, how did that happen? How is it that information about the island is not available at the boundary of ADS? What went wrong in the argument that you were giving? Because I spent some time saying, in a theory of gravity, when you have gravity, information in a bounded region is also always available in its complement. Now here we have gravity that's coupled to a bath, but at least here we still have gravity, right? And yet we are saying the information in the island is in this radiation region, therefore it's not available in the boundary. So what happened to our statement that, ADS is holographic, okay? Or all theories of gravity are holographic? Okay? Is the question clear, I hope? Yeah. We seem to have a counterexample to this argument that in gravity, all information is localized. It is always available at infinity. Okay? Kiran, is your question from now? You have a question from now? Or is this hand raised from earlier? I'm assuming hand was raised from earlier. Okay, great. So now let me point out, however, it's not a counterexample for the following reason. Okay. When we couple, and this is something which is important to remember, okay, when we couple gravity to a bath, the graviton picks up a mass. So, coupling to the bath leaves behind a non-standard theory, of gravity. Of gravity in the ADS region. What is non-standard about it? No Gauss law. Because once the graviton picks up a mass, you don't have any more a Gauss law in this setup. Okay. In all the arguments that we made, the arguments always relied, the fundamental thing that went into the arguments was the Gauss law, the fact that the energy could be measured at infinity. Well, in such a system, the energy cannot be measured at infinity. Juan, your question, yeah, go on.
Yeah, so interesting. How it cuts mass? Yes, and the other question maybe.
Sorry, so can you say once again what?
Yeah, it's interesting for me, like how the graviton picks up.
Yeah, I'm about to explain that. Yeah.
Yeah, and the other more simple. So it seems to me that the Iceland argument, it sounds different. So from this localized argument of the idea are different.
It's not different. It's consistent. It's just a different system. Everything is consistent. It's just a different system, and you're asking a different question.
Okay.
For the island argument, it's very important you introduce this non-gravitational bath, and then you ask some question about it.
Okay.
Such a bath doesn't, I think, exist in our world. When we have a black hole, we don't have a region where we switch off gravity. So, I don't think this model is very relevant for realistic black holes, but, you could ask this question mathematically, and then there's a perfectly good answer where you get these islands and so on. Now I want to explain this point of why is it that the graviton picks up a mass when you couple it to a bath. Yeah, go on. Is there a question? Gogula Krishna, yeah.
Sir, I didn't understand the part before you said the information was in the boundary, so it was able to flow through the radiation region. But I don't know when you say now you're saying when coupling to the bath leaves a non-standard theory of gravity.
That's right. So both you see, very good, excellent, thank you. In this case, this was a standard theory of gravity. There was no bath. So now information is at the boundary. Okay. Once I couple it to the bath, then in fact what happens is that the graviton will pick up a mass, as I'll show here, but the information is still at the boundary, and it flows in. So whatever information about the black hole was here, it's already here and it flows in. Okay. After you have coupled it to a bath and you've allowed the bath to come to a steady state, the island appears at late times in this setup. Then by that time, this theory of gravity is not a standard theory of gravity anymore. Now, after you have coupled it to a bath, so this is late in step 2. Remember I said there's step 1 where you didn't have a bath, then there's step 2 when you coupled a bath. Now you've done step 2 and you've waited for a long time. Now, it is no longer the case that all the information in the gravitational region is available at the boundary of the gravitational region. It was the case earlier, when there was no bath, that all the information in the bulk of the gravitational region was available on the boundary of the gravitational region. After you couple it to a bath, that does not remain true anymore. Earlier, the question we were trying to ask was, there was some information which was originally inside the black hole. How did it enter the bath? And we explained it by this two-step process. Now the question we are trying to ask is, well, now it turns out that some information about the middle of the gravitational region has now gone into the bath. So it's not available at the boundary of the gravitational region. How is this consistent with our arguments? And I'm about to explain now. By coupling it to a bath, you created a mass for the graviton, and therefore our arguments no longer apply. Okay. Is this
So
clear?
like the island information was created after coupling to the bath then.
Island is always created after coupling to the bath. Exactly.
Okay.
Yeah, the island only appears after you've coupled to a bath. Yeah, go on. Yeah, John. Yeah.
And my question is, why would the graviton having a mass mean that it could go essentially jump to this radiative region? Because wouldn't the
so go on with the question, please. Yeah.
Because wouldn't the mass mean the gravity doesn't travel as far, and so
So graviton having a mass doesn't make anything jump. You see, the information. Let's go back to this two-step process. The information was available here. First, there was no bath. Okay, so all the information about the bulk is available here. Let's say there are 10 qubits of information here. All of them are available here in some scrambled form. Now I couple it to a bath. Of those 10 qubits of information, 2 qubits flow away. Okay, they go into the bath. Now they were in some scrambled form, but there was some infalling matter that's still here, right? So earlier, what was I saying? I was saying you had to equate some operators here with some operators here. There's one operator which could measure some information here. There's another operator which could measure some information here. It's not cloning. It's really you have to equate the operators. After you coupled it to a bath, which is here, you have to equate the operator here with the operator here. Because the information was here earlier, right? But now by this time, it has flowed out here. So now you're finding that the information it's just flowing from the bath. It was here earlier before you coupled it to the bath. Now it went into this region. But there's always one more copy. It's not a copy really. It's the same. There's another operator which can measure the information, which is still continuing to be in the middle. So earlier you were equating operators here. Now you are having to equate operators here. Okay. Is that clear? But this tells you that this information I is no longer available at the boundary of the gravitational region. So we were trying to posit a general principle, which is in any theory of gravity, information in a bounded subregion is available in its complement. What happened to that principle in this setup? Is it clear what I said? Okay, great. So I want to explain that this principle now doesn't work after I've coupled things to a bath because the graviton picks up a mass. I'm going to give you a quick argument why the graviton picks up a mass. Okay. Now let me see if I have a reference here. Well, let me give you a reference. 1 second. Yeah, the reference is, reference is, and in this, look for Poratis, look for papers by Porati. Okay. This is one way, one way in which this graviton mass was originally realized was by directly computing the back reaction of these kinds of transparent boundary conditions and the graviton self-energy. So you just do a graviton self-energy computation and you will find that, the graviton picks up a mass. Okay. I'm going to give you a quick argument. This quick argument is going to rely on some ADS-CFT. I hope some of you are familiar with the basic principles of ADS-CFT, but I'll try and explain as much as I can without that. But okay, I'll try. It's a much quicker way to get the answer that the graviton has to have a mass than doing this one loop calculation in the bulk. Although you can do the one loop calculation in the bulk. So let's go back to our two-step process, right? It's the boundary. Okay, in this boundary, remember there was earlier a stress tensor, and the stress tensor has the property that it's conserved. This is boundary stress tensor. The boundary stress tensor is conserved. In conformal representation theory, this is the statement that the stress tensor lives in what's called a short representation. Short representation of the conformal algebra. Okay. So what that means is it tells you that the dimension of the stress tensor is equal to D, and the stress tensor cannot pick up an anomalous dimension. Why can't it pick up an anomalous dimension? Because the dimensions of these so-called short representations, which have fewer elements than other representations of the conformal group, are fixed. They don't occur at all sorts of arbitrary dimensions. They occur at fixed dimension. In particular, the conservation of the stress tensor tells you the stress tensor lives in a short representation and tells you the dimension of the stress tensor is D. That's what tells you, by the way, that the bulk graviton is massless. Now, what happens when you couple things to a bath? This is old boundary. But now you have this bath here. Well, the stress tensor is still living here. I mean, it's an operator still. But now it's not conserved because clearly, energy is going to flow out, right? So d mu t mu nu is not equal to 0 in the presence of a bath. I hope this is clear. It's not equal to 0 in the presence of a bath because, the bath is added so that energy is not conserved, right? So that energy of the original system is not conserved. The original system has to lose energy to the bath. So clearly, d mu t mu nu is not equal to 0, but t mu nu is the energy, is the stress tensor of the original system. This tells you is not now in a short representation. Those of you who are familiar with the representation theory of the conformal group, this tells you the stress tensor, the primary has a descendant, which is whatever appears on the right-hand side. Okay. Earlier, it didn't have a particular descendant. That's why it was in a short representation. If it's not in a short representation, it tells you the dimension of the stress tensor is no longer D, but it's D plus epsilon. This is an anomalous dimension. Well, if you have an anomalous dimension, you now have a spin 2 operator which doesn't have dimension D, it has dimension D plus epsilon. Remember, the standard rules of ADS-CFT relate the dimension of the boundary operator to the mass of the field in the bulk. When the dimension of the boundary operator is D, the mass of the bulk field is 0. That's the standard duality between the graviton in the bulk and the mass of the stress tensor on the boundary. Now it's D plus epsilon. Okay. This tells you bulk graviton has a mass. Okay. Okay, I'll recap the argument. The argument is as follows. Look, ADS-CFT relates the dimension of boundary operators to the mass of bulk fields. The graviton is related to the stress tensor on the boundary. The dimension of the stress tensor is fixed to be, D, where D is the boundary space dimension. Okay, so is the boundary space-time dimension. It's fixed to be D, and that is, it cannot pick up an anomalous dimension. The dimension of the boundary stress tensor cannot change because it's conserved, and the conformal group, forces it to have that dimension. When you couple it to a bath, the boundary stress tensor ceases to be conserved. When it ceases to be conserved, there is nothing preventing it from picking up an anomalous dimension. It does, and therefore the bulk graviton picks up a mass. Okay. Juan, you have a question? Yeah.
Yeah, I would like to understand more about this terminology, the short representation.
Yeah.
So it means this first line, d mu t mu nu different to 0, it means
Yes.
that there's some descent then.
That's right.
But initially you said that it was 0, so there was not descendant. So what exactly? What is that? Why there were not descendant of the
Well,
stress?
sir, I don't. It'll take us too far into conformal representation theory to do this, but the main point is that the way representation theory works is you start with the primary operator, and then you have different elements of the conformal group. Okay, this d mu is what is p mu in the point in the conformal group. So the conformal group consists of the SOD. Well, the generators of the sphere on the boundary. And then it consists of translations you can make, and then it consists of special conformal transformations, which are called K-mu. Okay? And then the way you generate representations of the conformal group is you start with some lowest weight state, and then you act on it with other elements. And in this case, what you usually do is you take the lowest weight state to be annihilated by the special conformal generators, and then you act on it with the momentum generators. The momentum generators are these d mu's. That's how you generate representations of any group, actually. You start with some lowest weight state and you act on it with other generators of the group. So d mu is one of the generators of the conformal group, the p mu's. And you see, if the generator acting, it's not that all d mu's are 0. It's that when you contract this d mu with this, you get 0. And so it tells you a particular combination of generators acting on the primary gives you 0. And that's the statement that, some descendants don't exist. And now
some descendant. That's my some descendant. That's not good, but you may have some descendant.
Oh, right? Yeah. Of course. It has some descendants. Short representation doesn't mean that the representation has no elements. It just means that it has less elements than the usual number.
Okay, correct. Thank you.
You can see it's sum because there's a summation here, right? So if I just act with like D1 and T mu, that's okay. It's only when I sum that I get 0. So it's, yeah.
Right,
short just means less than usual. It doesn't mean nothing. Okay, good. So you see, because of this, the Gauss law doesn't work. Okay? So in fact, in standard theories of gravity, islands are usually inconsistent. And I want to give you one exception now. Inconsistent. Okay. So islands are not consistent in a standard theory of gravity, because if they were to exist in a standard theory of gravity, they would conflict with the principle that we had, which is in a theory of gravity, information in a region is always available in its boundary. The moment you have an island, it's telling you that, the complement of the island doesn't have information about the island. How can that be in a standard theory of gravity? Okay? It would violate the arguments that we were giving. Now, in these setups of where you compute the page curve, you have a massive theory of gravity, and therefore islands are consistent. But it's an unusual theory of gravity. It's not a standard theory of gravity, and it doesn't have a Gauss law. Okay. So in standard theories of gravity, islands are usually inconsistent. Okay. Now, I want to conclude. I'm almost out of time, but maybe I'll take 2 minutes more since I started a little late. I want to tell you just one example of when islands might be consistent in a standard theory of gravity. Right? You see, how did our arguments really go? What our arguments really said was that information, they were really, remember the arguments we were making were arguments in the asymptotic boundary. And what they really told us is that information that was available on some part of the boundary at later times was also available in a small time band. Okay? So the boundary neither loses nor gains information. That's what we really proved. Now it might be in some setups that the island is behind a double horizon. This is what's called a double horizon. By a double horizon from the boundary. When that happens, then, the island is, the information about the island never reaches the boundary. And therefore, it's still possible to have an island in a standard theory of gravity if it's behind a double horizon. It doesn't contradict the results that we have. However, this situation is also not relevant for a realistic black hole because, in realistic black holes, you don't have these double horizons. You never have information behind a double horizon of the kind that we have here. Okay. So this is one counterexample I want to give to this general statement I want to make, as I'm trying to make the statements as carefully as possible. But in a standard theory of gravity, islands are usually inconsistent. Okay, I'll just summarize, and then in fact, I'm going to stop. But let me just summarize what I said. Okay. In the last part, I've been discussing. So what happened?
So I wanted to ask about this double horizon. So in this case, hypothetically, the information that is not accessible to the observer at the outer horizon is, say, the information that started between the two horizons and fell in. Is that what the island is?
No, this information, this is this so-called bags of gold setup. These setups never occur for real black holes formed from collapse. In this case, the way you should think of it is you have some two theories, and these things are so so these kinds of situations are not situations you create by starting with some theory and creating a black hole from collapse. Okay, in this setup, there's some recent papers by Vijay Balasubramaniam and others where you can read about these islands behind a double horizon. These are as I said, these are cases where information about the island never reaches either this boundary or this boundary. Okay, it's just completely protected. So it's what happens when you take these boundaries and you put them in some mixed state. If you put them in a mixed state, then this island, in fact, is something that belongs to an external system, which is external to this gravitational system completely. Okay, so maybe I shouldn't have mentioned this. I just wanted to say, mention that there are some cases when, islands can exist without creating a contradiction with what we proved, and that's this double horizon case. Yeah. Maybe we can discuss it some more when we come back. I just want to complete a recap once, and then we can stop and discuss some more of their questions about this. Is that okay? If there are urgent question, we can take it now. Otherwise, let's just take it at the end. Okay, let me just recap what I said. So I've spent the last some time discussing the issue of page curves. I said that, look, the way these page curve the page curve originally is based on the same error if you apply it to usual black holes that the Hawking argument is based on, because it's based on assuming that the Hilbert space factorizes into two parts, which we know doesn't happen in a theory of gravity. Okay? So the original page argument is based on, not the original page computation of the Haar measure, that's fine for non-gravitational systems, but the idea that it can apply to a realistic black hole. However, if you decide that you do want to see the page curve, you can see the page curve by setting up the right kind of system. And that's what people have done recently. But what they've done is they've taken an ADS black hole and they've coupled it to a bath. And in the bath, you then ask, how does information flow from one part of the bath to the other part of the bath? If you do that, then you can see a page curve because you've switched off gravity in the bath. So there's no gravity in the bath. Okay? This is not in contradiction with anything that we said. In fact, the novel physical effects that we spent some time discussing tell us how information enters the bath. And the way you should think of it is, think of a two-step process where you first create an ADS black hole, then you couple it to a bath. In the first step, all information is at the boundary. In the second step, it flows into the bath. So it's not surprising that information about the interior ends up in the bath. However, you can now ask something more sophisticated, which is, well, information about the interior enters the bath, which means after some time, it doesn't stay near the boundary of ADS. So how could it be? Because we said all information in the middle of ADS lives near the boundary. And the answer is that after you've coupled it to a bath, then this principle is no longer true because this theory of gravity now becomes massive. It doesn't have a Gauss law. I gave you a quick argument from ADS-CFT telling you why the theory becomes massive. It has to do with the fact that the stress tensor picks up an anomalous dimension. If the theory of gravity had not become massive, then indeed we would have had a contradiction with our results. And so if you have a standard theory of gravity, standard meaning one where the Gauss law applies, in such a theory, islands are usually inconsistent. You cannot have an island, unless in some exceptional cases, the island is separated by a double horizon. But this island behind a double horizon story is not relevant for realistic black holes. And therefore, for a realistic black hole, I would say you should not think in terms of islands unless you have some way to model the non-gravitational path. Okay, so I'm already 5 minutes over time. Let me stop here. Thank you for your attention. And this brings us to the end of the lectures. Of course, we can have some more discussion now. Some of these questions, I have to say, are issues of perspective. Now, the fuzzball approach is a little similar in flavor to what we said, because it also says that if you keep track of all observables outside the black hole, they have information about the interior, about the whole state. The fuzzball approach, though, goes a little bit further. It says the black hole does not have an interior, right? It says, well, and if you read the fuzzball papers, they take the no-hair theorem as something which is given, and they want to solve the problem in classical gravity. So the microstate geometry solutions are really classical gravity solutions that evade the no-hair theorem. And the way they evade the no-hair theorem is, if you add an extra dimension, you can have an extra dimension that pinches off before the horizon is reached. And so you can get all sorts of geometries with the same masses and charges as the black hole, but which do not have a horizon. And then they want to say it is these geometries that actually keep track of information. However, as we've been discussing, you don't need to modify anything at the classical level to get rid of the no-hair theorem. The no-hair theorem fails automatically when you include quantum effects. And you don't need to postulate anything extra to say that information is available outside. It's a natural consequence of putting together the constraints of quantum mechanics and gravity. Okay. So I think that the fuzzball solution is physically along the right track in terms of saying that the wave functional outside has information about the interior. I don't agree with the idea that we should not have the horizon. The horizon is a semi-classical concept, and the effects that we are talking about are exponentially suppressed effects, and it's perfectly consistent to have a horizon, but not have but still have information outside, because the horizon is just asking about the expectation value of the metric. So that's what I think about the fuzzball approach. Yeah, what if we collapse the asymptotic region into the black hole? No, the asymptotic region can't. The asymptotic region, by definition, as I said, is fixed in a theory of quantum gravity. We don't try to collapse the asymptotic region into the black hole. So the asymptotic region, in all the discussion we said we are restricting to states where the asymptotics are fixed. We don't want to go and change the asymptotics. If we do that, then we should go even further out and say some other asymptotics are fixed. Okay. So that's maybe there's some way of phrasing the question, but in the precise results we proved at asymptotic infinity. And I did try to emphasize that it's important that the asymptotics, we don't allow them to fluctuate. That's why we can make these statements. If we don't talk of asymptotic geometries, but start talking of bulk algebras, then we could ask these questions, what happens if you make a bigger black hole and so on. So that's why we said something about asymptotics, which, in the mathematical framework, we don't allow to change. I think Harpreet has a question.
So if one get a wave function, suppose for a black hole, and show that is evolving unitarily in just finding out the scattering matrix, will it solve the problem?
Sorry, can you say once again, please? What?
Sir, if one get a scattering matrix and show that that is unitary, then that will solve the problem.
If you can compute a scattering matrix in the presence of black holes and show it's unitary, yes, that will solve the problem. If you can compute you have to compute a scattering matrix in the presence of black holes. Yeah, you're right. If you could compute that and show that, that's a very hard thing to do, of course, but yeah. I don't know if that answered the question, but yeah. One more question, which is, could I review the split properties? Yeah, I can tell you what the split property is. The following statement. It's a statement in quantum field theory. Okay. And let's create a buffer region, which is epsilon. Sorry. I want to make it thinner. The geometry doesn't have to be like this, where one region surrounds the other, but let's consider this case, okay? Then RBAR. Okay. Now, say there are two states, okay? The state one has a property. So let's think of some local operators, okay? Phi x1, phi xn. xi belong to R. Since you asked me to review it, I'm reviewing it in a very precise sense, okay? And let's think of some operators yi that belong to R bar, okay? And for any psi1, any states, psi1, psi2, there exists psi, this is the split property, such that if you compute the correlation in the state psi, phi y1 to phi yn, okay? Notice the kind of, now this has insertions in both places. Okay? This is equal to psi1, phi x1 to phi xn, let me call this m, into psi2, phi y1 to phi ym. What does this mean physically? Okay. Notice what it's saying. It's saying that the state for all probes in the region R, it looks like the state psi1. For all probes in the region R bar, it looks like the state psi2. And what is more, there's no entanglement between psi1 and psi2. If there was entanglement, the expectation value would not factorize like this. Okay. So it's saying it looks like the state psi, you give me any two states psi1 and psi2, I can find a state psi that has the property that an observer who's making measurements in R, thinks they're completely in psi1, and observers making measurements in R bar thinks they're completely in psi2. The split property crucially introduces a collar region here, epsilon. So, this is to deal with this issue we discussed of UV divergences. Even in a quantum field theory, the Hilbert space doesn't exactly factorize, but this is almost like a factorized state. It's almost like saying the state is psi1 times psi2, except that we have this collar region which helps you interpolate a little bit. It smooths out these UV divergences, okay? So split property tells you it's the precise version of the statement that the Hilbert space factorizes. If you say the Hilbert space factorizes in quantum field theory, various formal QFT people will come and tell you, oh, no, it doesn't factorize even in ordinary quantum field theory. But the statement is in ordinary quantum field theory, we have the split property, which is the precise version of factorization. You have to introduce this collar region epsilon. And in gravity, we don't have the split property. Okay? That's because if you give me these observables in R bar, they're enough to completely fix what's happening in R. That's why So Hawking's argument, I was saying factorization, but what it really assumes is the split property, and split property is false in gravity. Excellent. Are there any other questions, sir? Why does Gauss law only apply to standard gravity? Gauss law holds in standard gravity. If you have a mass, the Gauss law doesn't hold. You can check that for massive gravity, there's no Gauss law. Just like if the photon has a mass, there's no Gauss law. You can't measure the charge at infinity. Charge gets screened by the mass. So once you have a mass, you don't have a Gauss law.
And
Okay.
having a theory of massive graviton, it's not a serious problem in general.
I don't know what it means, whether it's a serious problem or not. In all these systems where you couple things to a bath, you have a theory of massive gravity. So it's appeared a lot in the literature, although without quite, emphasizing this fact that the theory is massive. Okay? But whenever you add a non-gravitational bath, you have a massive theory of gravity. Now you could say, is that a good model for our world or not? But
I mean that usually gravity is kind of long range interaction, and that's imply kind of massless.
I agree. Yeah, it's not usually appreciated that if you add a non-gravitational, I don't know, by now I guess it's appreciated. It was certainly not appreciated so much earlier that if you added a non-gravitational bath, it would also spoil the properties of gravity in the region. It would make it massive. Okay, I mean, it's a model. So these are models where the graviton is massive. Now, I don't know what it means to say it's a serious problem. It's a model where gravity behaves differently from the way it behaves in our world. Now we can discuss where the model is good for our world or not good for our world. As I said, there are different views on that, but yeah.
Some other technical question, maybe the last one. when we have suppose that we want to compute this quantum correction E minus S, which are relevant, but using this ADS-CFT and basically computing observable in on the CFT side. For example, if I compute on the two-dimensional conformal field theory correlation function, usually we compute the 4-point correlation function. What is this quantum correction? What are these quantum correction for this specific example?
Well, you would have to calculate those correlators up to accuracy e to the minus S. You would probably need to calculate S-point correlators to accuracy e to the minus S if you really wanted to do this, right? So if you really wanted to check in a concrete way by actually doing the calculation, it's a very hard calculation to do, of course. Yeah, the argument we are giving right now is it's formally that information is always there. But if you really wanted to do it, then you would have to compute S-point correlators to accuracy e to the minus S.
Yeah, and what is this so my question is like trying to understand what is this accuracy, how I know that I reach it, like.
Oh, it's well defined, right? Because S is the black hole entropy.
Okay.
So once you compute things to e to the minus S, where S is the black hole entropy, that's enough. So if you keep track of e to the minus S corrections, that's generally enough for you to be able to verify the state was pure. S is, oh, sorry, I should have been more clear. S, wherever it appeared here, was the black hole entropy. So it's a specific number. So in the case of ADS-CFT, S for big black holes, S is proportional to n squared. So you'd have to keep track of e to the minus n squared corrections.
And
usually,
then is the number of field, right? In the correlator.
N, no. N is the n, which is the ratio of L Planck to L ADS. It's the n of ADS-CFT. Remember this S is proportional to G Newton times something. So G Newton in the ADS-CFT setup is capital N. N is the n of the SUN theory. So you would have, it's not that you have to compute e to the minus 4. Even if you're trying to compute a 4-point correlator in a black hole background, you would have to compute e to the minus capital N squared corrections, which are non-perturbative corrections, to check this accuracy.
Okay. Thank you.
Welcome. Okay. But the argument, can we not make the bath be reflective? No. If the bath becomes reflective, then energy would not flow into the bath. So it's important the bath is, the transparent boundary conditions. In fact, the bath has to have a much larger phase space than ADS so that, you absorb energy from ADS. It shouldn't be that energy goes into the bath and comes back into ADS. That would create a very confusing system. You could do that, of course, but of course the graviton would still be massive and so on. In these setups, usually the bath is just taken to be infinite. You want the energy to go out, not come back. Okay.
Yes. Sorry, I have a question. So,
yeah.
Like, then how do we think about, let's say if a diary goes into the black hole, I mean, should the protocol involve like the one you mentioned, that we have to do something in the boundary, like that?
That's right. So you have to make measurements on the boundary. You could use this protocol, but you would have to make measurements at e to the minus S, as one was just asking, in order to extract this information.
Okay.
I'm not saying this is something which you should practically try and do. It's it's just like, if you burn a piece of paper, we can't actually practically reconstruct it, right? We want an argument to say, what is it that will allow us to reconstruct it? Usually, if we keep track of fine-grained information, we will be able to see, if you burn the paper, what was printed on the paper. That's what we're doing here. We're saying, look, here is an error in Hawking's argument in how information was localized, which tells us that in principle, the information is present in e to the minus S corrections, which is different from, of course, actually trying to calculate it.
Yeah, because like it seems in the Hawking's original calculation, you have this pure production and it's always thermal. I mean, like how
No. There's no mistake with that. You see, remember this pair production, it's not thermal. Whether the pair production is thermal or not, also you can only check once you go to e to the minus s. That's why we had the lecture on how close are pure states to mixed states. Just looking at the leading order term doesn't tell you that it's thermal or it's pure. Pure states can also have the same correlators. And it's only at e to the minus s that you can see the difference.
I see. Okay.
So sorry again, to make sure that I understood the previous question. It's true that this quantum correction in two-dimensional conformal theory are given by this C central char correction.
Yes, that's it.
Okay.
The e to the minus c. That's the central charge is a number. Yes, e to the minus c. Correct.
Thank you.
E to the minus number into c. So n square is the central charge. Correct.
Yeah. Okay. Thank you.